This video is the first in a series in which we explore chemical equilibrium. Until now, in our calculations with stoichiometry, we have been assuming that any chemical reaction proceeds to 100% completion. However, this is not always the case. It might be that due to poor operation in the laboratory, or maybe the reaction is very slow, you find that the reaction does not proceed to 100% completion. Okay? There's one more reason that a reaction might not go to completion, and that is that the reaction presents something that we call a chemical equilibrium. Okay, so think about the A to B reaction, okay, where A is the reagent and B is the product. What we can do to see if the reaction proceeds to completion is to plot how the concentrations of reagents and products change on time. Right, so that's going to be our plot. This is the concentration of A as a function of time. Okay, and for A, what we'll have is that if we start with an initial concentration that has this value at time 0, then as the reaction proceeds, then A will fall. Okay? And then we can also plot how the concentration of B, the B product, would evolve on time. And then what you would find is that B, at the start of the reaction, if you start with no B, then it has a value of concentration of 0, but as A is turning into B, then the concentration of B starts to increase, perhaps along this fashion. Okay. So in this reaction, what we observe is that after some time, which is indicated by this line, what we find is that the concentrations of reagent A and product B, this will be the line of A and this is the line of B, they do not change any longer on time. At this point, what we say is that the reaction has reached an equilibrium. There is an important condition in which equilibrium takes place, and that is that the reverse reaction B to give A has to proceed to some extent. Okay, so you have chemical equilibrium when the reaction is reversible. Again, the hallmark for chemical equilibrium is that you find that the reaction has not proceeded to 100% completion, right? There's still a substantial amount of A left, okay? And the concentrations of A and B do not seem to change on time, okay? So clearly that's not a reaction that proceeds to 100% completion, and the reason in this case is that the reaction is reversible, so B is turning to A as A is turning to B. Okay, now at the macroscopic level, something that we notice is that it looks like the reaction has stopped. Okay, there's no more A going to B, and those concentrations of A and B are not changing. However, at the microscopic level, there is a lot of activity taking place. And what happens though is that the rate at which A is turning into B is exactly identical to the rate in which B is turning into A. If we call these rate constants K sub 1 and K1 prime, okay, what will happen is that the rate of generating products, assuming that these are elementary steps, would be as follows. The rate to generate products would be K1 multiplied by the concentration of A, and the rate that returns the products back to reagents will be K1 prime times the concentration of B. So when you have equilibrium, what happens is that those rates, the rate to go forward and the reverse rate, will be exactly identical. And again, that means that even though at the macroscopic level we're seeing that the concentration of A and B do not appear to change on time, at the microscopic level those reactions are still happening, but the rate at which the reactions going from the left to the right are happening is exactly the same as the rate of the reactions from the right to the left. Okay, so at equilibrium what we have is that K1 multiplied by the concentration of A is equal to K1 prime times the concentration of B. That is when you reach equilibrium. Now, there are several ways to characterize the equilibrium. In this case, we have that the amount of B present is a little bit larger than the amount of A. Okay, so in this case, what we say is that the reaction seems to be displaced to the right. But we can envision some other types of reactions in which perhaps the concentrations would be a little different. Okay, so for example, imagine a chemical reaction in which there's a little bit of reaction initially, but then eventually A tapers off pretty fast, and then B tapers off also very fast. Okay, notice that in this particular example, you reach equilibrium perhaps at this point. Okay, that is equilibrium. And then you find that, well, there's been very little B formed, and there's a lot of A left. This reaction, we say that is displaced to the left. Okay, so the equilibrium can be displaced to the right, it can be displaced to the left, it can fall more or less in between reagents and products, and that is something that we will take care to characterize in future videos. Okay, this video has served to provide an introduction to the concept of chemical equilibrium.